Today we're going to talk about primal-dual interior point methods. So this is the second lecture we've had on interior point methods. Last time we talked about the barrier method. And I figured it was maybe just worth spending a few minutes reminding ourselves of the kind of hierarchy of problems that we've seen and the ones that interior point methods lie at the top of. And so just remember that we started off by saying quadratic problems are the easiest. These are problems of the form, minimize over all x, 1/2 x transpose qx plus, say, c transpose x. Those are the easiest, provided that q is positive semi-definite, because I can just take the gradient and set it equal to 0, and then I would have the solution. Right? That's just the first order optimality condition for this convex problem. And then the second level up was something like equality constraints. If we placed equality constraints on this quadratic problem, and so under an arbitrary set of equality constraints, ax equals b, we could also solve them in closed form just using the KKT conditions. Right? We just introduced a dual variable that corresponds to this constraint, ax equals b. We added up into the criterion v transpose ax minus b, say, form the Lagrangian, and then the KKT conditions basically only have two components there. It's stationarity and primal feasibility, and if we solve for those simultaneously, it's just one big linear system. So each of these have a closed form solution. Comes from solving a linear system. And then we saw one level up from this was to do smooth minimization subject to equality constraints. So this is swap out criterion with f of x. Okay, and in that case we use Newton's method. So instead of having a closed form solution, we use Newton's method. And Newton's method reduced this problem, so minimize f of x subject to, say, x equals b, with a sequence of quadratic problems that each had equality constraints, each of which we could get a closed form solution from because of this, just from the KKT conditions. And by solving the sequence of quadratic problems, we arrived at the solution. And each time we make a quadratic approximation to the function, that's the quadratic problem we're solving. It's a second order Taylor expansion to f at the current point. Okay, so it reduces the problem to a sequence of equality constrained quadratic problems. Okay, this is where we were at the start of the second order methods unit. The next thing we did was interior point methods, where we added inequality constraints. So suppose we had, hi of x is less than or equal to 0 for I going from 1 through m or something. So now we have two ways of solving this. We saw the barrier method last time. This time we're going to learn the primal-dual interior point method. Provides a different way of solving smooth minimization problem. Minimize some doubly smooth function f subject to inequality constraints and equality constraints. And so there's two ways. There's the barrier method, and there's the primal-dual interior point method. Both of these essentially reduce this problem to one without constraints, where we're only performing minimization of some smooth function subject to equality constraints, in which case we then apply Newton's method. So in each of these cases, when we try to solve the problem in question, we move down the hierarchy one and reduce it to a sequence of problems, say, or in some cases even like here, a single problem, but a sequence of problems that lie at the previous level of the hierarchy, and we know how to solve those. And that's how we solve the problem in question. That's just what happens with the barrier method. So we reduce this to a sequence of problems without inequality constraints. We got that by adding the barrier term. Right, we introduced what we called the log barrier term, or the log barrier function that corresponded to these constraints. It was essentially the sum of log of minus hi of x, and then we took the negative of that whole thing. So it's minus the sum of log of minus hi of x, which was a smooth approximation to the indicator function for these constraints. And by multiplying that by some constant and making that constant smaller and smaller, we've reduced it to a sequence of problems without inequality constraints. The Primal-dual interior point method does it a little differently. So when we learn it, you're not going to see that it explicitly reduces our problem to a new one with a criterion that doesn't have inequality constraints, but you can see that from the perspective of what we call the perturbed KKT conditions. So keep in mind that it is a different perspective on accomplishing the same goal. We're never going to write out a criterion that has a log barrier term, but we are still reducing it to a sequence of problems without inequality constraints. We just do it via what we call the perturbed KKT conditions. So I just wanted to give this review so that we can have this in mind. This kind of summarizes our second order methods unit, this whole picture. So the barrier method, which we learned last time, to say it just once more, given a problem of this form, right, an arbitrary, let's say, convex optimization problem where f and hi are all convex and smooth functions, it starts by recognizing that we can introduce this function we call the log barrier function corresponding to these constraints, which we denote by phi of x. It's given by minus the sum of log of minus hi of x. And we can think about adding 1 over t times phi of x to the criterion and getting rid of the constraints. Or equivalently adding phi to the criterion, but multiplying our original criterion f by t. And we're going to solve this problem with some value of t by Newton's method. And then we're going to increase our parameter t by a multiplicative factor, say 10, multiply t by 10, solve that new problem, and warm start Newton's method for that new problem at the solution that we found for the previous problem, the one that had the smaller value of t. And repeat that over and over again until we have the guarantee that m over t, where m is the number of constraints and t is just the parameter we're looking at, is less than epsilon. And once we've met that stopping criterion, we are guaranteed by the duality gap. We saw this last time. It was a very simple proof we put together. Via a duality gap argument, we are guaranteed that the iterate we found here, which we might call x star of t, is no farther away from the optimal solution in this problem in terms of criterion value than epsilon. So it's epsilon suboptimal. F of x star at the parameter t minus, say, f star, the actual solution to our original convex problem, is no more than epsilon. Okay, that was the barrier method. And let me pause for questions before we continue on with the Primal-dual interior point method. No? OK. So today we're going to talk about the barrier method from the perspective of the perturbed KKT conditions. And we're going to use that same set of KKT conditions to motivate what we call the Primal-dual interior point method. And then we'll learn how to do line search to choose the step sizes in the Primal-dual interior point method, which is only slightly more complicated than what you've learned in Newton's method, say, or gradient descent. And then I want to go through a bit of a highlight of the way that the barrier method and the Primal-dual interior point method differ when you apply them to standard form linear programs. So what are the differences between these two? I figured it would be worth just putting it right at the start so that you can keep the differences in mind. These are very similar. They're both what we call interior point methods. So when somebody says, I applied an interior point method, they usually refer to one of these two, the barrier method or the Primal-dual interior point method. But they have some key differences. So they both come from the perturbed KKT conditions. The barrier method, we actually saw it was motivated by the log barrier function. A different way of seeing it, which is what we'll cover just shortly, is from a perturbation of the KKT conditions for the original problem. But the primal dual interior point method, unlike the Berry method, it just takes one Newton step before it updates the parameter t. So it also keeps a parameter t that kind of controls the strength of approximation that you're making to the hard constraint. But instead of iterating Newton's method until convergence at a particular value of the parameter t, and then updating t, it just takes one Newton step. So that's a pretty key difference between the two, which means there's no difference between inner and outer loops for the primal dual interior point method. There's just one level of iteration. Another important difference is that the primal dual interior point method iterates. The points that we produce along the primal dual interior point method path are not necessarily feasible. So that's a big difference between the primal dual interior point method and the Berry method. And in particular, so they're going to satisfy the inequality constraints by construction, but they may not satisfy the equality constraints, and we may not have dual feasible points. That's maybe an even bigger deal. Remember, we saw that when we had dual feasible points in the Berry method, which we proved that every time you run the Berry method, at any point you can always get some dual iterates from the iterate x star of t, and they were dual feasible. And the reason that was so important was that actually gave us access to a duality gap. We computed the difference between the primal at x star and the dual at these dual feasible points. That gave us a duality gap, and that came out to be something very simple. It was just m over t. And so we had a kind of a bona fide stopping criterion, which told us that at any point we knew how to stop. We just stop when m over t is, say, smaller than or equal to epsilon. The primal dual interior point method does not produce dual points that are feasible, necessarily. Or so generically they're going to be infeasible, which means that we don't have a very good idea of how to stop, in the sense that we don't really have a duality gap. So we do something a little bit more heuristic. On the flip side, the primal dual interior point methods can often be more efficient. And this is not something we're going to cover in any level of detail, but they can often exhibit better than linear conversions. So remember, we saw that the Berry method last time we had a theorem that said that it converges at the rate of log 1 over epsilon if you want an epsilon suboptimal solution. That's what we call linear convergence, if you recall, in the optimization kind of lingo. Primal dual interior point method can often do better than that, but that's a very there's like a very kind of detailed analysis that's required to see that, and it's not something that we're going to spend any time on. So if you're interested, then take a look at the monograph written by Nesterov and Nemirovsky on interior point methods. I have the name of it at the end of the slides. Okay, this was an enormous topic of research, by the way. Primal dual interior point methods, once they became, once they kind of made their introduction in optimization, there was a huge following in terms of people implementing them and also studying them theoretically. The last difference I would say is that primal dual interior point methods are less intuitive. So I personally have a harder time remembering the primal dual interior point method steps than I do the Berry method, because the Berry method you get from just taking the constraints, wrapping a log around them in some way, and then applying Newton's method. So, you know, if I'm out of practice with interior point methods, I feel like the Berry method is the one I typically remember first. The primal dual interior point method is trickier, and so we're gonna see it in detail today. But those are the main differences. So let's go back to the perturbed KKT conditions, and let's recall that the Berry method can actually be seen as solving a problem that does not correspond to these KKT conditions, but corresponds to kind of a slight perturbation of them. So if we go back to the KKT conditions for the original problem, this problem here, this convex problem, minimize f subject to hi of x is less than or equal to 0, and ax is equal to b, then they are as follows. I have the stationarity condition, which just comes from taking the gradient of the Lagrangian and setting it equal to 0. And remember, here I'm assuming that f and hi are smooth and convex. That's why I can take gradients and not subgradients. So that's just the typical stationarity condition that we see for our problem. Ignore the second line for now and look at this. This is complementary slackness for the original problem. Just tells us the dual variable corresponding to the constraint that hi of x is less than or equal to 0 has to either be 0 or the constraint has to be tight, or both. Okay, that's complementary slackness. And the last two in that block are just primal and dual feasibility. Those are the KKT conditions for our original problem. The barrier method we saw last time. We went through the check of this. It was simple. It really solves a different version of the KKT conditions, where complementary slackness is actually replaced by this second condition up there in that block, which is ui times hi of x is equal to minus 1 over t for I going through 1 through m. So in other words, I don't require that the product of my dual variable and hi be exactly 0, but something small and something with the right sign, because hi of x should be less than or equal to 0 if x is feasible, and ui, which is my dual variable, should be non-negative, so it should be less than or equal to 0. And so here we're just saying that it's something close to 0 if t is large, but not quite 0. And we saw that this actually came right out of the log barrier function. Really, this comes from the fact that the derivative of log of x is 1 over x. So when we differentiated the log barrierized criterion and we defined the dual variables appropriately, we saw that actually the log barrier method solves this system of equations rather than the original KKT conditions. Okay, and as I make t larger, this complementary slackness condition is getting closer and closer to my real one, and so I'm getting closer and closer to solving the right set of conditions, the KKT conditions. Are there any questions about that? Okay, so we didn't cover this last time, but the Newton updates for the log barrier problem, so if you were to think about the updates to the log barrier problem, I can think about that as taking this system of equations. This is a system of equations in x, u, and v, and trying to approximately solve that by taking a linearization of that and setting it equal to 0. And that's how you can derive the barrier method steps, as if you first substitute for the dual variable ui minus 1 over t times hi of x. That's not something that we covered last time, but it's something we're going to actually cover when we talk about standard form LPs at the end, so see it in detail for that. But said differently, let me just write that down for you so it's a little more transparent. I can summarize the perturbed KKT conditions as follows. Let's just call it there's just some function of x, u, and v that I have equal to 0. And for that, I'm going to grab stationarity and the perturbed complementary slackness condition, and I'm going to ignore the inequality constraints for now. So this R just really has a block for the, oh, and also I'm going to stick in the equality constraint that ax is equal to b. Okay, so I'm going to stick in all of my equality constraints into this. Actually, it's up on the slide here. You can see it. So I have stationarity, I have the perturbed complementary slackness, and I have my equality constraint. That's R of x, u, v. And if I could solve that, and I also had that at the solution, I had hi of x is less than or equal to 0, and u is bigger than or equal to 0, then I've solved the perturbed KKT conditions, right? Because that just incorporates all of the equality constraints. And because this is a nonlinear equation in x, u, and v, it's nonlinear because, look, I'm multiplying here, for example, a diagonal matrix of u times hi of x. That's all of these terms, ui times hi of x. And I'm also multiplying ui by the gradient of hi of x. So it's not a linear set of equations in the variable x, u, v, so it's hard to solve. We could take a linear approximation to this and set that equal to 0 and solve that instead. So what we do is we say that if I were to take a step in the direction, say, delta x, delta u, delta v, and I want to figure out if I'm at x, u, and v, what step I need to take delta x, delta u, delta v to make this 0 to solve the perturbed KKT conditions, I can approximate that by a first order Taylor expansion, which is just given by taking the derivative matrix at the point x, u, v and multiplying it by this direction. delta x, delta u, delta v. And instead of solving for the direction delta x, delta u, delta v that made this exactly 0, I can actually solve this instead, which is a linear approximation to the KKT conditions. And if I were to iterate this, and I were to, before I solved for the update direction here, substitute in u to be minus 1 over t times h of x. So maybe this is how I'm going to define u for each I. That's just making a variable elimination in this system of equations, which came from just the middle block, right, which was easy to solve for u. Then I get the Berry method. So substitute in this, solve for delta x, delta v, and repeat. These are actually the Newton steps. In the Berry method. Okay, so what we will do this for standard form linear programs at the end of the lecture, so you'll see kind of a little more detail about that. But I wanted to point out that for the Berry method, it's another way of viewing what it's doing. Take the KKT conditions, take a perturbed version, set it equal to 0, and then try to solve that nonlinear system by doing Newton's method, but for root finding. Right? We can also do Newton's method as a way of finding the root in this system of equations, the update direction that makes this equal to 0. Okay, so Primal-dual and interior point methods also use this strategy. The only thing they do differently is they do not substitute in for u. So Primal-dual and interior point methods do not make this substitution. But they're the same strategy other than that. So here they are. Let's look at them on the slides. We're going to write the KKT conditions, everything but the inequality constraints, concisely as r of x u v equal to 0, where r is a function that takes in the primal and dual variables and produces a big vector. And the first block of that vector is just the stationarity conditions. And I've just written the gradient matrix, or rather the Jacobian of this function h as dh of x. So all this is that on each row, I have the gradient of h1 with respect to x, and the second row the gradient of h2 with respect to x, etc. So dh transpose u is nothing more than the sum of ui times the gradient of hi at x. It's just a concise way of writing that, plus a transpose v. So if I were to set this equal to 0, this would be the stationarity condition. The second set of equations is the perturbed complementary slackness. So this is just a diagonal matrix with u on its entries. So this is saying that ui times hi of x must be equal to minus 1 over t for all I, if I set this block equal to 0. And the last block is just the equality constraint in the primal, ax is equal to b, if I were to set that block equal to 0. So the KKT conditions, the perturbed KKT conditions, without the inequality constraints, are nothing more than setting this function r of x u v equal to 0. And because it's a system of nonlinear equations, I think about solving it by taking a linear approximation and solving that linearized system of equations, and then iterating that until convergence. Yeah?
Sir, since you are using Newton's method to solve a non-linear equation, you need to consider the region of convergence.
Yes, I mean, this provably converges, but we need to do backtracking. So we're not going to be doing something like pure Newton's method. We're going to need to do backtracking. So we're going to find an update direction and this delta y, but we're not going to necessarily take a step fully in delta y. We'll update So y here is my abbreviation for the triplet xuv. We'll add maybe t times delta y, or I shouldn't use t, s times delta y, where s is a backtracking parameter that's been chosen, less than 1. Okay, so just to give a bit more details, I think that it's pretty much what I wrote in the paper, but we maybe can have a little more details in the slides. If we were to define y to be the triplet xuv and delta y to be the update direction, then instead of solving for the update direction that makes this exactly 0, which is difficult because it's a system of nonlinear equations, I approximate this KKT condition by a linearized version. So I take r of y plus the Jacobian times the direction. Jacobian is nothing more than the gradient, but when the function you're looking at is vector valued rather than real valued. Right here, I'm thinking about h as a function that goes from Rn to Rm because I have m inequality constraints. Okay, so each inequality constraint function I've stacked on one of the components of this function h. And if I were to define these three quantities, R dual, R central, and R primal, these names are really not super important. This is just saying that the vector R dual, R central, and R primal just gives me the value of my perturbed KKT conditions at the point xuv. Then I can solve for a particular update direction, and that will give me the update direction when it comes to linearizing this KKT condition. Okay, so we said that we want to make 0 equal to, let's say, r of y, which is this triplet, r dual, r central, r primal, times the Jacobian times the update direction, delta y. And now I've just written out here what I've written out in block form, the Jacobian of r of y, or the derivative matrix of that function, with respect to the block variable xuv. So just recalling that r of xuv is equal to the following. Okay, that's r of xuv. Here I've shown its derivative. So the first column gives me, the first row gives me the derivative of this function with respect to x in the top left, and then u in the middle, and then v in the right of the top row. So the derivative of this first block with respect to x is just what I get when I take the stationarity condition and differentiate it once more with respect to x. That's given up there. It's the Hessian of f plus sum of ui times the Hessian of hi. The derivative with respect to u is nothing more than just the, it's linear in u, so it's just the gradient matrix of h. And then with respect to v, it's just A transpose. That's the first row. I do the same thing for this. I differentiate with respect to x, u, and then v across the components of the second row. So I get minus diag of u times the gradient matrix of h. And then with respect to u, again, it's just linear in u, so this just becomes minus diag of h of x. And there's no v, so that's 0. And then in the last row, it's the same thing, but now I'm differentiating this with respect to x, u, and v. And there are no u and v, so that's why the last two components are 0. And it's only linear in x, that's why I have an a. Okay, so if this matrix calculus looked like a bit confusing to you, if maybe this was a surprise, then spend some time thinking about where this gradient matrix came from. And you can always go back to, for example, the element-wise prescription of each of these quantities. That may be easier. Like instead of thinking about it as minus dag of u times hi of x, you could think about this as the sum of ui times hi of x. And differentiate that with respect to x and also with respect to u, and that's why you'll see what those first two rows are. Okay, so there are, I guess, multiple ways to approach matrix calculus. The most tedious, maybe the most straightforward, is just to do it element-wise. Okay, so this is what we've done. We've taken r of y, and we've approximated it at the point y plus delta as the gradient matrix times delta y. And now, in order to solve for update, we have to set this equal to r of xuv. Actually, this is minus r of xuv, so there should be a negative sign here. Just missed the sign. And once I solve for this, this is the Primaldual update direction. So the reason it's called the Primaldual and shared point method is because here we are actually explicitly solving for both primal and dual variables, right? Because we've written down the KKT conditions, which contains primal and dual variables, and we're explicitly solving for both of them in this iteration. Just to repeat, the difference between this and the Berry method is that the Berry method first eliminates u from this system before it forms this linear approximation. So it really only makes an update in x and v. Any questions? Okay, so these are different updates from the Berry method because it matters whether or not I make a variable substitution or I eliminate a variable before I take a linear approximation. Those don't give me the same thing. Approximating a function by a linear function or eliminating a variable and then doing so lead to different outcomes. So these are actually genuinely different updates than those from the Berry method. And like I said, I think this is also a bit less intuitive in the sense that it's farther away from what we've learned with Newton's method, but it is still trying to solve the KKT conditions. It just does so via two steps of approximations. The first is to perturb them a bit, change complementary slackness, and the second is to solve a linear approximation to them rather than solve them as written, because it's too hard to solve them as written. So that's what the Primaldual and shared point method is doing. So with no questions, I guess we'll just continue on. This is not the easiest topic that we'll learn across the semester, so make sure to interrupt me if you're finding something confusing. Good question. Where's the t? I'm asking you, where's the t? Yeah. Right. So it's in the right-hand side. So remember, this was the basically the value of the KKT conditions at the current point xuv, which contains t.
But we update with a solution that no t all the process.
No, so it does contain t, right? So we have, this is the right-hand side of the linear system we're solving. It contains t. It's just that the leading matrix in our linear system itself doesn't contain t. Doesn't mean that this is not going to depend on t. So the update direction will depend on t, right? Because it's given by this matrix inverse times this vector, and this vector itself depends on t. It's, like I said, this is the state of the perturbed KKT conditions at the point xuv. That's what these r's represent. It's a good question.
If we take t as infinity, will it be some different? Why we cannot? The original form has a t as infinity. Why we should define finite?
So do you agree that there is a difference mathematically between taking t equals 1 and t equals 10? Like I will not get the same. Do you see that there's a difference in terms of the update direction? It's because this right-hand side, this thing, call this B, this whole thing B. Call this whole matrix M. Okay, so I have M times delta y is equal to B. So delta y is M inverse B, but B depends on t. So is delta y. The update direction is going to depend on t. So you're going to get a different answer with different values of t. Now we'll get to, I haven't talked about how t is updated in the context of the algorithm yet. I just defined the step. So you'll see how t comes into play in a few slides. We haven't actually described the algorithm. We just described its update direction. Yeah.
Is there some numerical reason why R central is defined to be negative diag deviation of x minus 1 over t as opposed to just plus plus?
That's a good question. So your question is, if I were to multiply, I guess any of these equality constraints, if I were to multiply them by a negative sign, then they wouldn't change. So why do I necessarily? Yeah, Han, do you have a? Correct. Sorry? Correct, yeah. But it's still a valid equality constraint if I were to just flip the sign here in this equation. I don't know if there's really a difference. In fact, I don't think there can be, right? Because the negative sign, that is, you just would be redefining what it means to, you'd be redefining the meaning of delta y or something. Right? I could flip the sign of any of these equality constraints arbitrarily. Like I could flip the sign of the stationarity condition but leave ax equals b. And so I'd get a minus sign for all the first terms, but I'd have ax minus b for the third block, and I think it would all be the same.
Yeah, because your ER would also have that negative sign.
Yeah.
I was just wondering if it was more numerically stable to do it that way or what. I don't know how, but
Yeah. I don't think so, yeah. It's just sorry?
Is the minus sign because we want to make the big equations
No, it's always going to be because it's, yeah, I don't think that's going to matter. I think it's somewhat arbitrary. I think that if I were to take the opposite of one of these equations, then it would basically effectively cancel out once I take the gradient. Because the corresponding component of the matrix M is going to be negative, and so when I solve for, it's like solving for a minus sign on both sides of the equation. You're not going to get anything different. It's going to be the same. Yeah?
Can you use this method to solve the original KKT condition?
Well, we are doing that. I mean, essentially, right? We're just solving a version of it where we've changed complementary slackness.
Yeah, but can you just solve the original KKT condition instead?
Okay, so that I'll leave you to think about how that's different from Newton's method. So suppose we didn't have inequality constraints. Is that different from Newton's method? So if we didn't have any, let's see if somebody can guess that. If we didn't have inequality constraints, what's the difference between applying Newton's method and just linearly approximating the KKT conditions over and over again? So there,
the problem doesn't have any quality.
yeah. Yes, you can kind of see from this, it's the same thing. So, I mean, another way of saying that is that if, suppose I didn't have any constraints, equality constraints or not, I can either think about Newton's method as minimizing f, or I can think about it as solving the linear system grad f equals 0, right? By taking successive linear approximations to that. It's doing the same thing. So we are really doing this when we do Newton's method without inequality constraints. But with inequality constraints, I don't think there's any way to avoid this kind of this perturbation to complementary slackness. No, that's not going to change. And that just depends on how you update t then. I mean, if you updated t differently, then it doesn't matter how you parameterize that. Yeah?
But basically, the whole point of letting it be 1 over t is that you can get closer. It's a warm start sort of thing rather than just. Because I think the question was why not just let ui hi equals 0 and then do the method on that.
Uh-huh. Yeah, so
But I think we answered that in the barrier method.
Right. So I think it's the problem is not smooth enough if you were to not, that's right, to take the right-hand side of the complementary slackness equation just to be 0 in order to apply Newton's method efficiently. I think let's hold off on maybe questions about the algorithm itself until we actually present it, because I think it'll be clear once you see what happens. You can think about the Primal-dual and cherry-point method as being a version of the Berry method which only takes one Newton step, and so stays a bit away from the central path, but it has a similar idea. So we're also trying to follow some kind of central path, but we're not really dedicated to being very close to it, because we're just taking one Newton step. And with that in mind, the connection to t is kind of clear. It provides some smoothness to the problem. So the idea about applying Newton's method to this original KKT conditions, it doesn't work for the same reason that it doesn't work to take the barrier parameter to be absolutely huge to begin with and just solve that problem. So thank you for suggesting that. So are there any questions about the update direction? That's really what I want to make sure is clear. The algorithm itself we're going to go through, and I think you'll get some more insight for its steps. Just the update direction. So does everybody understand the update direction, or at least maybe could implement this? Right? It's just a linear system that you have to solve. Okay. So before we talk about the method, I want to introduce the surrogate duality gap for Primal-dual and cherry-point methods, which is not a real duality gap because especially the dual iterates are not necessarily feasible. So it's not really a duality gap, but it's a useful quantity nonetheless. So recall that for the barrier method, we saw that by defining, in fact, just this definition for the dual variable, once I have primal iterates, these are automatically feasible, dual feasible. And I could get a duality gap by evaluating the difference between the primal criterion at x and the dual criterion at g of u, g of uv. And that ended up being m over t at any particular step along the central path, where t was the parameter that multiplied the log barrier term. And that was a way that advised us how to stop. So for Primal-dual and cherry-point method, we cannot really claim that we have a similar construction for the actual duality gap, because the dual iterates that we see along the way, these u's and v's, they're not necessarily feasible for the dual problem. So it doesn't give us a proper lower bound on the primal criterion, and so evaluating the difference between f of x and g u v isn't really a duality gap. But what we tend to do is we tend to check it anyways, and in addition to that, check how far from feasible we are. And those two things together inform us when to stop. So the duality gap is actually, it's very similar to the one we constructed for the Berry method. And in fact, if you take ui to be minus 1 over t times hi of x, you'll see they are exactly the same, right? Because in the Berry method, ui is always defined to be minus 1 over thi of x. In the Primal-dual and cherry-point method, that's not so. We actually solve for ui as part of this KKT system. We didn't substitute it out first. And so it's not going to be necessarily just minus 1 over t times hi of x. But the same form can give us a surrogate duality gap, which we call eta. Okay, it's minus sum of ui times hi of x. This is always going to be, this quantity is always going to be non-negative as we run the algorithm, because we're always going to constrain ourselves to look at points such that hi of x is less than or equal to 0, and ui of x is bigger than or equal to 0. Okay, so it's not a real duality gap, as I mentioned, because u is not necessarily feasible. And so it doesn't necessarily inform us when to stop. But as we see in the next slide, we're going to stop when this is small, and we check the kind of the amount of feasibility violated by the dual variables when that's also small. So when we're close to feasible and the surrogate duality gap is small, we can kind of heuristically claim that we're close to the solution. I mean, it's more than a heuristic, because there are convergence proofs for Primal-dual and cherry-point method, but as far as we're concerned, this is not an actual duality gap. So here's the method. Maybe it's helpful just to jump right to the method. With Primal-dual and cherry-point method, we start with a feasible point x, So this is one that has it's actually strictly feasible. It satisfies hi of x is strictly less than 0, and ax is equal to b. And we start with a u that's strictly bigger than 0, and just any v. Okay, and so these are, with superscripts 0, these are all of our initializations for the variables x, u, v. And we define this surrogate duality gap, eta, to be just the sum of minus hi of x times ui. It's written in vector form minus h of x transpose u. And we select a barrier parameter, mu, just like we did with the barrier method, which we use to multiplicatively update t. So we're going to, after we take one step with t, we're going to multiply it by mu. So think of mu as like 10, for example. So we're going to repeat the following steps. I'm going to define t to be essentially mu times what it was before, but it's really mu times the surrogate duality gap over m. And OK, let's just leave it at that. So this is how I initialize t, for example. I'm going to compute the primal dual update direction delta y by solving this linear system, solving this big linear system. That contains, remember, delta x, delta u, and delta v. I'm going to determine a step size s via backtracking, which we'll cover shortly. And then I'm going to update y according to where it was before, plus s times delta y. So this updates the triplet of x, u, v, all primal and dual variables together. Then I just recompute the surrogate duality gap. Okay, this is it's the sum of minus hi of x times ui. And I stop if that's small, say it's smaller than epsilon. And both primal and dual residuals are small. So remember, the r primal was how far I'm away from satisfying the equality constraint in the primal. And we called this r dual, how far this is away from 0. The stationarity condition is away from 0. Why is that called r dual? How does that relate to dual feasibility? It's a bit subtle, and maybe nobody spoke up when I said that u and v weren't necessarily dual feasible, but we are maintaining that u is bigger than 0. So why is uv not necessarily dual feasible? And why is that called r dual? I call these residuals, by the way. This is the primal residual, ax minus b, and r dual is the dual residual. So what are the two conditions that are placed on u and v as part of the dual? The first is that u is bigger than or equal to 0 and v is anything. There's that. There's also the implicit condition that u and v are in the domain of the Lagrange dual function. That's one that often, remember, it puts in constraints into the dual that aren't explicitly written when we write u bigger than or equal to 0 and v anything. And those that constraint of u and v being in the domain of the Lagrange dual function is actually expressed up there. So if this is equal to 0, so this is true if and only if x minimizes L of x uv over x, right? In which case we have guv is actually equal to L of x uv. And so if x minimizes the Lagrangian, then by construction, by definition, this was not minus infinity. Right? Because spots where this would go off to minus infinity, we actually encode in as specific constraints in the dual. And this means that u and v must be in the domain of the Lagrange dual function. That's why that's called a dual residual, for that reason. OK, so back to our method. We stop when the surrogate duality gap is small and also the primal and dual residuals are both small. So we're close to being feasible in terms of the primal equality constraints and whatever the dual constraints are for our particular problem. Remember, there are going to be generically more than just u bigger than or equal to 0. We saw that with linear programs, with lots of other duals. You introduce constraints that come in as part of the domain of G. Any questions about the method before we talk about backtracking and just some intuition with LPs? I'm sorry? I don't think so, right? Because we have oh, I think you're right. So I have this backwards. So T is equal to eta over m. No, I think that's correct. So I have it the right direction here. Oh, yeah, of course. Sorry. T is equal to m. I guess I couldn't. Division escaped me there. So yeah, it's m over eta. So thank you for pointing out on this slide, and also in the next slide, it's m over eta rather than eta over m, which makes sense because as we proceed with the algorithm, the surrogate duality gap is going to get small, and then t is in effect going to get large. Okay, let's take a quick, maybe couple-minute break, and then we'll come back and talk about backtracking, and we'll get some intuition when we talk about linear programs as well.